All right, well, let's get rolling. Who wants to go first in terms of giving updates?
I don't have any updates. I just wanted to see what was going on. Oh, here's oh, cool.
Okay, all right.
So I can go.
Go.
So I couple things, pushed the Pytherium fork choice rule, but there was actually a major refactor of the state revamp branch, where it's essentially isolating the different consensus mechanisms. So you can kind of like, pick your consensus.
Nice.
That was something that Vitalik did, and but it did break a lot of the previous Casper tests that we have, and so just like refactored it so it works with the new repository, and so now it is essentially taking the fork choice, modifying it a bit to improve it and kind of have it a little bit cleaner, and then integrate it back into the largely refactored Pytherium state revamp branch. So that's basically what it's, more progress on in the development front of just getting this ready for the reference implementation and Casper daemon.
Cool. That's awesome. That sounds really good. Did you want to post the links?
Yeah, sure.
Good idea. Cool. Yoichi, any updates?
Yeah, I was on vacation last week, but I attended a Bitcoin Wednesday meetup in Amsterdam. I talked a bit about this minimal slashing condition verified, and then I got questions like if somebody bets on both forks, blah blah, and then I was answering like if you bet on both forks, well, the fact you are cheating would be provable by anyone, so you are punished on both forks and so on. So yeah, that was my activity around Casper.
Cool. That's I'd like to hear about that work in more detail at some point.
Oh, okay.
Yeah, for sure. Do you have links?
Yes, I have links to no, I haven't uploaded the slides yet, but I can send you this minimal slashing condition thing.
Yeah, that would be great. That'd be great. I'd really appreciate that. Well, I've got some updates. It's a bit of a deep dive just on one piece of the stuff I've been talking about. I'll do a quick screen share. Hang on a second. Let me find the Zoom thing. Okay. So if people remember from last time, I was talking about this setup here. Where is it? Yeah, okay. So I was talking about the requirements for types, and I talked a lot about the double perp close condition, but I didn't talk a lot about the fee here, which is an additional filter on the types that are given. So in order to prove that the the trace in a trace nodal category implies consensus, and consensus implies trace. I need types which are the objects in the category, and those types are triples. And we talked a lot about the sigmas and the taus, but we didn't talk about the middle element, the phi. So now I'm going to talk about the phi part, and I'm going to give it in terms of a simplified version. You can find a fairly detailed version in the namespace logic papers that I published in 2005. But here I've been working on a much more automated version of that. The namespace logic system was done entirely by hand. I mean, I knew I had an algorithm to calculate that kind of logic, but that particular logic was produced by hand calculation. Here, we've now produced the ladle algorithm, and so the work that Mike Stay and I have been doing. One other piece of background to make sense of all this is at the time in 2005, I was working largely with model theoretic conceptions of the logic. So in terms of the category theory, I was looking only at the types or the objects of the category. I wasn't looking at the morphisms. The morphisms in the category are proofs. And so when we give a category theoretic interpretation or presentation of the ladle algorithm, we sort of have to reconcile the proof theoretic side or theorem proving side with the model theoretic side. And so essentially that's what's being done here. And for simplicity, I start with a much smaller calculus. The row calculus is tiny already, but I start with a combinator set to make it even simpler and smaller. And it turns out, so we published a couple of papers recently that they're on arXiv, and I put the links up here before. But what they do is they eliminate all of the nominal phenomena from the calculus. So by nominal phenomena, I mean we eliminate all of the names, ports, channels, everything. That's all eliminated. And so the fees will be given in terms of this calculus here, and the relationship between the row-lang contracts and this calculus is that you can compile the row-lang contracts down into this calculus, and that's basically just factoring it through the row calculus, and then the faithful translation that there are two faithful translations that Mike and I have published. So basically there are two forms of these combinator calculi. I won't go into too much detail about the calculus because there are papers now up on arXiv. But essentially the calculus is straightforward. It's an asynchronous calculus with and it's heavily inspired by Yoshida's combinator calculus for the pi calculus. The main difference is that she fundamentally depends upon new and replication. So in the history of these things, there's the SKI combinators, which eliminate variables in the lambda calculus. And then she takes the idea of abstraction elimination from lambda to SKI and applies it to pi to get prefix elimination, but she still fundamentally depends upon new and replication. And we eliminate new and replication using the row calculus trick of reflection. So essentially we have the atoms are, the stopped process, a process which can be thought of as sending a message, a process that can be thought of as duplicating. So whatever you receive on A, you duplicate between B and C, a process that kills all inputs coming to the channel A, a forwarder from A to B, branching right, branching left, and the S combinator. So then, and then these are your atoms, and then you can also you can take a name and turn it back into a process, and you can put two processes in parallel. And you might be interested in, well, how do names arise? Well, names arise as the codes of processes, but new names actually get created in the branch left and branch right. And there's a set of rewrite rules. So I won't go through all of these, but just as an example, when you have a message that's running in parallel with a duplicator, then it gets forwarded off to B and C. So it turns into two messages, one to B and one to C. Likewise, for the process that kills, a message that's running in parallel with kill just turns to 0. A message that is running from when you send a message P on A and that's running in parallel with a forwarder, then it becomes a message of P on B, and so on. So all of these are written out and they're published in the paper. Now, what's not in the paper is this new work. And this is largely just the application of the ladle algorithm to this setup. The important point here is that we have a notion of subtyping, and we have a notion of specialization. And that's critical because we can now talk about subtyping in a concurrency setting, and that there's a whole raft of literature on the difficulties of the notion of subtyping in a concurrency setting. So there's the whole concurrency inheritance anomaly, sort of cottage industry, where many people independently discover that inheritance and concurrency don't mix, and then they come up with different proposals for how to solve this. The more general idea is, how does subtyping, as opposed to inheritance, fit in a concurrency setting? So here we have a proposal laid out, and it fits with Méliès and Zeilberger's proposal for subtyping in a categorical setting. Okay, so the basic idea is we have a notion of derivation. So we start with two basic types. There are terms, which are the terms that are generated from this grammar, and there are names, which are the names that are generated from this grammar, right? So, and those two just happen to be recursively interdefined. We have types. Given those two built-in types, terms and names, we have some additional types which are built up recursively. So in particular, suppose you've got 0, well, then 0 is of type term. Suppose you've got, so this is the notation for derivations. The left-hand side of the double arrow is the term formation context, or the typing context necessary to conclude the right-hand side. For 0, you don't have any context to determine that 0 is a type term. If you knew that A was a type name and P was a type term, then you could form a term, MAP, just like we have here, sending P along A, and that would be of type bold M is a type NT. And similarly, for all the rest of these, right? So you just follow the constructors here, and you get a similar kind of construction. So if you know that A is of type N, B is of type N, C is of type N, then you know that you can form this term DABC, and it is of type D, bold D, N, 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 right? So it's no big surprises. The only one that's kind of interesting is the parallel composition, and you're going to have specific parallel composition rules. Okay, and this is going to correspond to a notion of cut. All right, so in particular, for all the left-hand sides of the rewrites, you're going to have these kinds of term formation rules, and this is going to allow us to control concurrency in the way that we want. So, given that delta, so one way to read this is that the context thinks that this is the case. So, given that delta thinks that D is of type D, N, and N, and gamma thinks that M is of type M, NT, then if you had both of these, the delta and the gamma, then that context thinks that the par is of this type, where we introduce the tensor type here. Now, so far so good. Nothing super interesting here. More or less exactly algorithmic. Now we introduce a notion of kinds, and this is where the ladle bit comes in. So the ladle stands for logic as a distributive law, right? So what we do is we push the given some monad M. So this is a distributive law between two monads. Well, there's a monad in operation here, which is the monad that's associated with the Levere theory that gives this little term calculus, right? And then there's some monad that's going to represent collections of terms and or collections of names. And we don't really care what that monad is. So we'll just call it M, and then we say that the set of kinds is parametric in that monad. So that monad could be set, that monad could be list, that monad could be tree, pick your favorite monad. We don't really care. In general, in order for it to be a useful notion of collection with filtering so that you can support a select from where kind of construction, monad plus is kind of the minimal spec on the monad. So that's what's useful. And then we just follow this grammar here, and we push the monad through. So you have, but remember, this is at the type level rather than at the term level. So you'll have T, but then you'll also have all of the constants. So the only constant here is 0. So you'll have T, the original term, and then you'll have the constants, and then you'll have all of the term constructors. And then finally, you'll have the monad constructors, which is the last thing here. And so this gives you not the types, but this is like a scheme for producing all the types. So this gives you the kinds. So a type is an element of this grammar or this production. So in general, you'll have a term satisfies a type, and a type satisfies a kind. So this is quite a bit richer than a lot of type systems you're likely to see. And now we push through this idea of essentially what is a kind of Méliès-Zauberger subtyping through the derivations. So in particular, we still have, you need no context to determine that 0 is a type term. But if you had that a particular name M is of the kind at phi of M, and you have that a term is of the kind phi of M, and you have that A is of type N, so this is some subset of names. In other words, this is a namespace, and you have that A lives inside that namespace, and you have that P is of type T. So remember, this is some type T is a type. So this is a kind, that's a type. So P inhabits that type. Then you get to conclude that MAP is of type bold M in some namespace T some type. So you can compare that to this less interesting rule up here. So this less interesting rule just basically says, you know, when you form a message, it's a type message, right? But down here, we're now saying when you form a message under the constraints that you can only send on this namespace, and you can only send messages that conform to this constraint here, then you get, you know, a message, the message type namespace message shape. That's a more interesting rule. And remember that this is in the context that this is these kinds of things over here are the fees over here, and then the terms here are essentially the processes that we're typing via these types. So they're a kind of very, very simplified core Erlang contracting mechanism. And you just follow the same construction all the way through for each of the derivations, right? So that's what happens there. And then finally, we have the rewrites or the refinements of the cut rules. So if you know that alpha, which is going to be a kind, is a type. If you know that alpha is a subtype of beta, so essentially over on the model theoretic side, what that means is that this is a subset of this, or this is a sub-collection of this, where M is providing the notion of collection. And we have a nice definition of that for all monads. That's different than the sub-object classifier idea. Okay, so if you have this, and you have that delta thinks that this term here is of this type, and you have that. So in other words, we don't really care. You know, you would really have some namespace here, and you'd have some namespace here, but this is a sort of a cut rule scheme. So this is going to work for all namespaces here, but we don't really care which ones they are. So I just write out the kinds here. And you know that gamma thinks that MAP is the type M alpha, and again some constraint on P's. Then together, delta and gamma think that you can put these two in parallel, and you get this tensor type here. Now it's important, right? This is kind of important. This subtyping relation here is important. What it's saying is the duplicator is accepting messages in a wide range of options, right? So it's willing to duplicate messages out to B and C from a menu from a namespace here, and the message has to live inside that namespace. That's what this constraint is, before you can put these two together. And so you can see how this begins to constrain the behavior of the processes. And the other important point is the way this works like cut. So notice that we end up with the left-hand sides of these rewrite rules. So we have all these rewrite rules, and here's the first one, right? And when we go from the left to the right, we're going to expect to get something like this. So we're going to have cut elimination rules that correspond exactly to the rewrite rules up here. So so you'll be able to take a proof that is a sequence of these steps like this, and you'll be able to apply to the proof the rewrite rules. So we'll get at the categorical level, we'll get morphisms that take these kinds of things. So there are two morphisms, because we can think of this as a morphism, and we're going to get two morphisms which rewrite the conclusion down here to not be the duplicator with the message, but in fact the two messages here. And then we get a kind of cut elimination theorem, but it's because the calculus is not confluent, you don't have the property that cut elimination always terminates, or that that it's a function. So you don't. It's not going to. The cut elimination is not going to behave in the way that cut elimination behaves, say, in the intuitionistic calculus. I mean, the intuitionistic logic, right?
I have a question.
Yeah, please.
Before the termination, do the rewriting rules preserve the types?
Yes.
So, when you
I'm sorry. Preserve the types on the left hand and right hand side? No, they do not.
Oh, okay.
Yeah. So that's kind of important. Right? So notice that the type on the left hand side will be of this type.
Mm-hmm.
Right, but the type on the right hand side will be two messages.
Yeah, so I was thinking about that. So when you do cut elimination or type to lambda calculus things, usually
it has subject reduction theorem, and that's not going to apply here.
Okay.
Yeah, so the system is not confluent. It doesn't apply. It's a different kind of system. It follows as what we're suggesting is that there's an underlying structure between the two that is common, but it's fine. I mean, when types describe behavior of processes, it's usually, when the process evolves into something else, the type changes as well. That's kind of normal. So yeah, exactly. Yeah, that's correct. Good observation and great question. Yeah, thank you. Cool. So that's kind of the work I've been doing. It's a little bit of an update. Sorry if that was too much detail, but it's kind of fun stuff. Any other questions, comments, thoughts?
Seems cool to me.
Thanks, Carl. Thanks. Yeah, no, this part is really fun because we have one of the things that we were pleasantly surprised by was just how natural and easy the proof theoretic side comes together. Basically, without the category theory, I'd be flailing because there are just too many design decisions when it comes to creating these kinds of type systems. But with the category theory, many of my design decisions are just nailed down. I just don't have any choices, and you can kind of see that as you look over the construction. There's not a lot here that can where there's a lot of wiggle room, and the category theory is nailing down like 98% of the design choices in terms of the type system. So it's very clearly algorithmic. And the other thing that makes this important from my point of view is it means that I can potentially get a speed up, because in order to check that, what we were going to do was do type checking as model checking. So I just go through the namespace logic model checking algorithm when it comes to checking these fees here. But here, notice that we do in fact have a type checking algorithm. So you read these backwards, and you get a type checking algorithm. And it's not Hennessy Milner, but it is certainly an algorithm. And so it is potentially a significant speed up over the model checking algorithm that we had before. It depends on how much of the cut elimination goes on in a particular presentation of a type. So I think that will be a particular win performance-wise. So that's the other implication of carrying out this work. Cool. Any other updates, conversation, discussion we want to? If not, we can yield back 21 minutes.
Cool.
Awesome, guys.
All right. Thank you very much.